And what it does is give them a set of labels. Here, for example, the label A, the label 1, and the label love or heart. A species produces some set of structures. And the name of the species is what structures it should produce. So it's like a machine. So for example, if I look at the species, I would like to define a species of permutations. And yeah, I should stress names are very important in species. So a lot of the work is finding good names for species. So if we would like to have a species of permutations, we feed it 3 labels, A, 1, and heart. And then the output is 6 elements. So the first element is it maps, so I write permutations in 2-line notation. A should be mapped to A, 1 to 1, and heart to heart. That would be something like identity or so. Or here, A is mapped to heart. No, that's not what I want. A is mapped to heart, 1 is mapped to A, and heart is mapped to 1. That's something like a cycle. So I rather think of permutations as bijections, actually. So that's a perfectly good definition. Another example is the species of set partitions. So the input is again a set of labels. Yeah, and the square brackets are there on purpose. You will see in a minute why. And the output are the partitions of this set into subsets. So we can put all of these into a set. We can put A and 1 into a set and heart into another set. Or we can put everything into a singleton set. That's something easy. Or as a third and last example, species of linear orders, L. We just arrange the elements in the set in all possible ways. So of course these are again 3 factorial elements, and they look very similar to the second line in the permutation species. Okay, so that's a definition. It's not really good because it's very hard to compute with it, because it's a gadget. Yeah, okay. Oh, sorry, there are some more examples I'll speak about later. So graphs, you could think of a species which produces for you all graphs where the vertices are labeled with the labels you put in, and all vertices should have a different label, distinct labels. And let's say they should be simple, because we want finitely many as output, and yeah. Or rooted trees, and each vertex again has a label, and the labels should be all distinct. So one thing which is important, the set of structures should be finite, so we can do something. Yeah, I missed finite here. So that's a definition, but not a very good definition. And the good definition is as follows: a species is a functor from the category of finite sets with bijections to the category of finite sets with maps. And this means that's the definition. This first line is the definition, but maybe you don't like categories, that's okay. So I spell it out for you. And yeah, well, categories were invented to define functor. So I spell it out for you, it's easier, okay? Don't be afraid of categories, you can forget them again. So given a finite set of labels U, F square brackets U is the finite set of F structures on U. And for a bijection sigma, from U, from some finite set U to some other finite set V, F square bracket sigma from F of U to F of V is the relabeling of structures. So this relabeling has to satisfy two properties. If the bijection I plug in is the identity map from U to U necessarily, so if V equals U, then the resulting relabeling should do nothing. It should be the same thing. And if I compose two bijections, the relabeling of the composition should be the composition of the relabelings. And that's exactly what you should expect. Yeah? So you have a graph and the vertices are labeled, and now you relabel them. You specify for each label a new label, let's say prime. Yeah? You have the labels A, B, C, and the new labels should be A prime, B prime, C prime. And what you do is you look, do I have A somewhere? Yes, and I replace this A with A prime. That's the way you could think of it. Okay, and it's much better to think of labels as something you cannot compute with. So it's good to think of labels as A, 1, heart, and maybe some Indian letter. Yeah, this is something you should not think of the labels as 1, 2, 3. That's not so good because then you tend to order them, for example. And A1 and heart you cannot order in some good way. Okay. Oops, excuse me. Someone got lost. Yeah. And as I already said, usually the precise definition of relabeling is obvious. I mean, you can define some very obscure esoteric species where the relabeling, you actually will have to state what the relabeling does, but usually it's obvious, and that's the power of species. So what we want to do is we want to play, and we don't want to think. That's the deal. Yeah. So here's another example of relabeling. We had already the species of set partitions of 3 elements, and now I'm relabeling A to X, 1 to Y, and heart to Z. So this is the bijection. Here I specify the bijection, and here I specify a structure. So A and 1 are in one block, and heart is in one block, and I replace all the A's here with X's, all the 1's here with Y's, and all the hearts with Z's. Okay, and yeah, and that's the reason why I use square brackets here, because it's tradition to, also, it's a good idea to use very different kinds of parentheses, brackets, curly braces for different things. So just that you don't get confused. Square brackets means I expect labels, or because it's a functor, I expect a bijection. Okay. Okay, are there any questions so far? Maybe not. Okay. And if I have a new mathematical structure, I may also want to say when two things are the same. And again, a very difficult or very complicated. Excuse me. This is actually something useful. We say two structures are in the same species. So F is my species. Two structures S and T are isomorphic if they are obtained from each other by relabeling. And here you see why the species of permutations and the species of linear orders are somewhat different. If I apply this relabeling to this permutation, I obtain, well, I replace all the 1's by 2's, so these two 1's become 2's. I replace all the 2's by 3's, so these two 2's become 3's. And I replace all the 3's by 1's, so these two 3's become 1's. And now I put this in normal form. This becomes the permutation 1, 3, 2. If I do the same on linear order, so here's my linear order 2, 1, 3, that's the second line here. I replace all the ones by 2 and so on. I get something different. Okay, so yeah. Isomorphism of structures actually has a meaning, there's an interesting thing, yeah. And now I can introduce the F tilde species, which is the species of structures with automorphisms. And you can think of it as n factorial times the number of isomorphism types. So some permutations here, S is for symmetric group. Some permutations are very similar, they have the same cycle type. Yeah? So if I have one permutation and another permutation, they have the same cycle type, I can obtain one from the other by relabeling or conjugation if you prefer. And so S tilde is, so to say, encodes the cycle types for you, but as a species. Okay. And we can also say what it means that two species are isomorphic, not structures, but species. Well, if there is a natural transformation alpha from F to G, and it's best to think of, how should I say, they produce the same things up to relabeling. That's how you should think of it.
Just a quick question to see if I'm understanding what you're saying. So if you take F to be the species of permutations, then perm tilde would consist of a permutation and another permutation that commutes with it.
Possibly. Perm tilde would be
yeah,
permutations tilde. So I call them S for tradition's sake.
Yeah, S.
So it would consist of a labeled of this object together
with another permutation that commutes with it, right?
No, which fixes it. Actually.
Fixes means commutes because the action is by conjugation.
That's right. Yeah.
So, yeah. Okay. Yeah. Thanks.
Okay. Okay, and as we just saw, S and L are not isomorphic because relabeling works in a different way. Okay, and now something interesting, which I like a lot. Maybe you have seen group actions before, and it turns out a species is just the same thing as a sequence, an infinite sequence of group actions of the symmetric groups. So let's recall what the group action is. So we have, here I mean actually a finite group acting on a finite set F is a homomorphism from the group to the permutations of this finite set, or equivalently a map which takes a group element and an element of my finite set, and it sort of transforms this finite set in some sensible way, namely that this sort of, I don't know, action law holds. Okay, so in our case, so for species, this little, let's do an exercise. What, in the species world, what would the little f be? Or what would be the capital F in the species world? Excuse me? No. It's the set of structures, right? Yeah. In the species world, the capital F would be a set of structures, and actually we can prove this in one line. We just define the group action as we apply a capital F to the permutation G excuse me, we define the relabeling, so the group action is the relabeling of a structure. That's what it does. Okay, that's how these two things are connected. And you may be surprised, I just told you, you shouldn't think of the set of labels as the set 1 to n, and now I do this. Well, I do this because here we have the symmetric group on the letters 1 up to n. It's easy, it's not hard to see that you can go back and define the species given the group action. That's quite possible.
Another question. But it depends on the choice of bijection from 1 to n to u for every u, right? I mean,
yes.
You have to choose this. And
you have to choose this. This is completely correct. But the essence of species is that the set of labels is actually not that important. Yeah, you don't want to be able to order the set of labels, for example. It's just there to distinguish things. Yeah, that's an excellent question. Thank you. Yeah. Okay. And just as for species, we can define when two group actions are actually isomorphic. Possibly I've seen this before, and I will not read it because it's the good way to think of it. It's just the same as when two species, when the functors are isomorphic, or the proper language would be naturally equivalent. Yeah. So yeah, well, actually I can say it. So two group actions are isomorphic if there is a bijection alpha which commutes with the group action. That's what this is saying. Oops, excuse me. Other questions so far? Okay. And now the interesting, playful part is we can actually compute with species. So we can say what it means to add two species. Well, this looks strange. So the addition of two functors from the category of finite sets with bijections to finite sets with bijections, or maps, that's the same thing, is if we apply it to some set of labels, we compute the F structures on this set of labels, and we compute the G structures on this set of labels, and then we take the disjoint union, which for tradition's sake is here denoted with plus. So the good way to make them disjoint, we have to make these two sets disjoint. We sort of remember from which species it came from. So we indicate a little f or a little g, something like that. Okay? For group actions, that's just the direct sum. And the product works as follows. We take our set of labels u, and we split it in all possible ways into two parts. Yeah? So we take and choose two subsets. And then we put an F structure on the first subset and a G structure on the remaining subset. And then we take the Cartesian product, or you could say an F times G structure is actually a pair where the first element of the pair is an F structure, the second element of the pair is a G structure, and the total set of labels is just the original set of labels. Okay? And we will see later why this is called induction product. Or actually, I can state it for those who know a little bit of representation theory, or some actually quite some representation theory already. It comes from inducing from a Young subgroup to the symmetric group. Okay, and these two are very interesting or very nice operations on species. The most interesting operation is plethism or composition. So we can say what it means to apply one species to another. The correct word is of f of g. An f of g structure is obtained as follows. You have your set of labels, and now you take a set partition of your set of labels, and on each block you put a G structure, so the inner structure, and on the set of blocks, which is also a set, you put the F structure. And we will see an example. This the natural language works well for this. So if you say f of g, it's what you should, what it is, what you would think it might be. And there are lots of other operations on species. The Hadamard product or Cartesian product. It's sort of, you can think of, you write the labels in the middle, and then both species on both sides share the labels, so to say. Yeah, it's not that important. So yeah, there are lots of other operations which are not that important, and I won't talk about them.
So I can. Thanks. So I'm regarding your previous theorem where you said that species are equivalent to a set of group actions,
yeah.
Sequence of group actions. So if I have a species which has no symmetries whatsoever, so there's no group action.
Linear orders actually.
Then I mean, I could think of many things that have no symmetry, right? I mean, I could, for example, maybe compose partitions with with permutations, or I could do all kinds of things. Mm-hmm. Then I don't see that this is equivalent. You see what I mean? I mean, there could potentially be many things, many species which have no symmetry but are distinct. Is that?
Yes. So there could be many species. Yeah. So that's true. Yes. So.
But then doesn't that contradict?
No.
Why? I mean, for example, take permutations, union, partitions.
A group action. So actually, yeah. So with bullet n come two things. So one thing is the symmetric group on n letters, but also the second thing is this capital F, and we have a little n here. So each group action comes with its own set.
I understand. So
yeah.
So okay, maybe I ask you later.
Okay.
Yeah.
Okay. Yeah. And then let's go through some special species. So I should add, these species were invented in Quebec, where they speak French. So all the letters are French. So E is for ensemble, which means sets. And what it does, it just returns the set of labels. So for every n, for every grade in my sequence, there's just one structure. No matter how big the set of labels is, I will be given only a single structure. But there is a fortunate coincidence. You can think of E also as exponential. This also works. And yeah, okay. Oops, excuse me. So C is the set of oriented cycles. So you just, for a set of labels with n, for a set of n labels, you get n minus 1 factorial structures. X of u is the singleton species. There is actually only a structure if you put in one label, and otherwise there will be no structure. So I never said that there have to be structures. The set of structures can be empty. And there is also the one species which only has a structure if you plug in no label. And why is it called one? So it's the unit element for multiplication. And yeah. And now this computing works very well. Oh, I made a mistake here. This should be a curly X. So the set of the species of linear orders you can write actually as the infinite sum of x to the power of n. So it's the geometric series, and it's very easy to figure this out. But so what you think is, so what does x to the power of n mean? You take a singleton, you take another singleton, and another singleton, and so on, and the total set of labels must be everything. Must be your set of labels you put in. And since these are tuples, so we started with pairs, but if I take a power, I get tuples. The order matters, the order in which you add them. And yeah, I said for composition, the right pronunciation is off. So a set partition is a set of non-empty sets. And that's obvious. If you want to prove it, that's actually not quite obvious. Yeah? But so François Bergeron, who sort of popularized combinatorial species, said the proof is say it out aloud. That's, yeah, a set partition is a set of non-empty sets. Or similar, a permutation is a set of cycles. It just works.
You also say draw a picture.
Sorry? You should draw a picture. I was very lazy, I admit. But I leave drawing the pictures as an exercise. So, yeah. Yeah, do you want me to draw pictures? Then I draw some pictures on the blackboard. I think there are no Zoom participants anymore.
Yeah.
Sure. Does someone want me to draw pictures? One person suffices.
Yes.
One person.
I love pictures. I'm a combinatorialist.
So.
I love pictures.
So how does f plus g of u work? Actually f plus g is the one thing which is not nice. I will do f times g. That's so you have your set of labels. That's how you draw them. You should think of them as all distinct, and then you partition them somehow into a set V and a set W, and the whole set is U. And here you put an F structure on them, and here you put a G structure on them. A different way to do this picture is you draw the labels on a straight line, and the V sort of selects some of these labels, and the W takes the other ones. Yeah. That's how you could think of a F times G structure, or an F of G structure is actually the same thing, just with a set partition. So I'm not sure whether it makes sense that I draw it. I'll do it anyway. you put little G structures here, and you put a F structure on these. So these pictures are, so there, I should have said, there is a very nice book by Bergeron, Labelle and Leroux. Combinatorial species. And tree-like structures. Where you find zillions of examples and pictures. Okay. Yes. Okay, I skip over this. Now the Sage part, because this is Sage days. Species are actually in Sage. So there is a package I developed together with Ralf Hemmeke a very long time ago, I think in roughly 2005 or so, in FreeCAS or Axiom. And Mike Hansen ported this package to Sage at the very beginning. And the special thing about this package is that we spent a very long time of how the user interface should work. And that sort of separates it from some packages, from some other packages, as in Maple, for example. And how does it work? Well, the entry point, the entry point is species, and you do a dot, and then there's a catalog of pre-defined species. For example, the permutation species is predefined, and then you can actually use as a functor, essentially. So you can ask for the structures on a set of labels. You get all the structures, and you can ask for the transport of structures. So you need, it's in Sage, unfortunately, it's slightly clumsy, that because of some limitations, but it sort of works. Yeah, you plug in a permutation group element, and Sage actually does what it should not do. It assigns an order to the set of labels. But you have to fix this order. And actually, it's the order you provided at the very beginning. So you plug in a list. The structure of the package is very nice. There is one unfortunate thing. It is very buggy. And so this talk is actually an invitation to fix all these bugs. So while preparing this talk, I noticed that this is wrong. So can you tell me why? You might need pencil and paper. So I take the last permutation, and so this should be read as A maps to C, B is a fixed point, and C maps to A. So we have a transposition CA, or AC. And now what we want to do is we want to apply the cycle. So this should map A to B, B to C, and C to A. Yeah. So in any case, this is, it's the inverse.
Gay sign conventions.
Excuse me?
Or gay left-right conventions.
It's the yeah. So it should be. So let's go through it. A maps to B. So just imagine. I have a blackboard. So the last element is CBA, which means CBA, or I like to draw it as A goes to C, and B is a fixed point. And now our permutation group element says we replace A by B, B by C, and C with A. So actually, C should be the fixed point and AB should be the transposition. And if you use the question mark, or actually if you use trace in Sage, if you debug it, you see immediately where it goes wrong. It's just a dyslexia. Yeah. So these bugs are actually fixable. Yeah. Okay. For another example, a rooted tree is a root together with a set of rooted trees. So here we see a set of rooted trees, and we remember the label which is the root. A tree is a pair consisting of a root, and the rest of the labels are distributed in a set of rooted trees. We cut away the root, and then we get a set of rooted trees. And actually this works. So we say A is just any combinatorial species. We don't say which one. We say X is the singleton species, E is the set species, and then we define A as X times E of A. So the first line is just, so to say, to declare the placeholder. And yeah, and then you can actually compute the structures. So if we want to have a tree on the set of labels A, B, C, you see the pair is denoted as A star something. So then it says what the F structure is. So the A is belongs to the X, and everything in parentheses is the E of A. So you can read this long thing as a set of A's. The F structure is just a set. We have two labels left, namely B and C. And the G structures are again trees. So here we choose B as the root. Here we choose, yeah, it's just one tree actually. Here we chose B as the root, and then another tree, and so on. Yeah. So here we have just one G structure. So we can draw the tree.
This is A goes to B goes to C.
This should be A is the root of the big tree, and then below that we glue onto it another tree with root B, and the tree rooted at B, well, it consists only of the C. So like this, and this is the root of our total tree. Actually, that's exactly the example we had yesterday. Yeah. Okay. Is there a question?
Can you say again what F structure and D structure means?
What it means that it's an F structure or in the composition?
I mean, do F and G refer to something specific?
So here we have this composition E of A, sets of trees. So the F is our E, the F species is E, and the G species is A. So the generic definition of composition was F of G, and here we have the special case F is sets and A is rooted trees. Is this the question? Or is the question, what is an E structure? What is a...
I mean, this was my question. How you're related to this example.
Yeah. So that's what I... Yeah. So F is sets here, and Yeah, we cannot write, technically we cannot, it would be nice if we would give the name here, but yeah, we could actually. We could require that this has a name, and then we could do this, yes. Yeah. So one takeaway is if you have a very combinatorial object, if you have something which you can express as a species, you can actually generate them in a very easy way. This is not efficient, of course, but it's efficient on your time, because I mean it's just 4 lines of code. It's not quite as efficient as the talk on React and moving graphs. This was very impressive, Julian's talk, but it's still quite efficient, yes. Okay, are there any more questions to this? How this works? Okay. Excuse me? That should actually be possible, yes. That should be possible. That's a good idea, to give a graphical representation of structures. That should be possible. Because for plus, at least for some operations it will be impossible. But for some operations it might be good to find a good representation.
Is what you have done.
Yeah. Okay, one way to use species, possibly not the most interesting, but one way is that we can assign generating functions to them. And remember, I insisted on the square brackets for the species. So for the generating function, it's customary to use ordinary parentheses. So the exponential generating series of a species just counts the number of structures in each grade, for each size. Yeah, and I used short notation. So if I use square brackets n, I usually mean the set of labels is 1 up to n. I shouldn't have done this. And of course, this is also implemented for example, for the set of trees we just defined, we get x plus x squared and so on. So the set of structures is, the number of structures is 1, then we have 2 because we have to multiply by 2 factorial, then we have 9 and so on, so it's n to the power of n. Okay? And actually, as a convenience, for convenience, we provide a shorthand which just gives you the number of structures. And yeah, I didn't say it, I should have put this slide before. Actually most of the operations we define on species work in a natural way also on the enumeration side. So plus is just plus of species, and then take the generating function, the exponential generating function, is just plus on the generating function side. The same goes for times, the same goes for composition, the same goes for derivative, pointing, and so on. Yeah. So this is very nice. And what's more interesting is you can also enumerate isomorphism types. So I defined this F tilde species before, or sort of defined, I didn't go much into it, but so the number of isomorphism types of a set of structures is just, you take the F tilde species instead and divide by n factorial. Oh, and there should be vertical bars here. So I mean the number of tilde structures. Excuse me, please. And then you get the so-called ordinary generating series, which we denote as we should. And of course, this is also implemented in Sage. So for example, for permutation, we get just these three representatives of isomorphism types. So we get the identity, so three fixed points. We get a transposition at a fixed point, and we get a cycle. And there are no other isomorphism types. For linear orders, we would get all six of them, because none of these are isomorphic to each other. There's no way excuse me, I made a mistake. There's of course only one isomorphism type. For linear orders, you should get only one. Please check all my statements in Sage. Yeah. Okay. We would also like to enumerate the isomorphism types. And this turns out to be nice for plus and nice for times, but for the rest it's not nice. In fact, the information contained in the f tilde and g tilde generating function is not enough to produce the generating function for the isomorphism types of the composition. So you need something more. And this is the so-called Frobenius character or cycle index series, which is, if you know some representation theory, just when you go from representations of the symmetric group to Schur functions. That's exactly what's happening here. So it's a complicated definition, and I don't expect you to memorize it here. The best way to find out is to do some representation theory, actually. But this symmetric function contains enough information to obtain the exponential generating function, to obtain the generating function of the f tilde species, and in particular also contains enough information to find out what the number of isomorphism types of a composition. Okay, and these are actually well-known specializations of symmetric functions. So this is very natural in a sense. I should stress the cycle index series does not determine the species. You can have non-isomorphic species which have the same cycle index series. And this is quite interesting because it's, as I said, it goes from the species to the character of the corresponding representation of the symmetric group. So this is just a character. But if you have a group action, you can have different group actions which correspond to the same representation. So this is not enough to get the group action back.
What is the simplest counterexample?
It's a species on, I think, three labels. I don't know. I can produce it for you.
Okay, so it's not some commonly known species.
I don't think you can possibly produce something, but it's not.
Yeah.
It's not. So I don't know one by heart. That's how I should put it.
But
Okay.
you'd also define the species f tilde, right? So
Yes.
Is it true that if f tilde is isomorphic to g tilde, then that's stronger than?
Well, the difference is, do you want isomorphism of group actions or isomorphism of representations? And isomorphism of group actions is something more refined than isomorphism of representations.
I see. Okay. Thanks.
That's the point. So and that's actually something mathematically interesting for representations of the symmetric group. we have symmetric functions, so that's the Frobenius character, and it's very nice to play with symmetric functions. You can do lots of things. For group actions, there is something called the Burnside table of marks, or the Burnside ring. So you can also compute with group actions. Okay, this is not very new for you, because I just told you you can compute with species. But there is no such thing as a nice object like symmetric functions, or at least I don't know of one. There's no nice way to encode group actions. Group actions correspond to conjugacy classes of subgroups of the symmetric group. That's the way to think of it. Okay. So now let me pass to excuse me, things which are actually not in Sage. So, and that's the invitation. And so now, if you want to have projects, I'm going to present 5 things I would like you to work on with me. So a rooted tree is a root together with a set of rooted trees. We had this before. And in general, we had A dot structures to give you all the F structures. And we have dot isotypes to give you representatives of the structures for the isotypes, for the isomorphism types. So it would be very interesting to have the isomorphism types for rooted trees, because these are the interesting numbers, the more interesting numbers. But boom, it's not implemented. And the reason is it's actually not quite easy to implement this. What you would need to be able to produce representatives for isomorphism types is to actually generate isomorphism types for young subgroups. You have to go a little bit further. And this is something we definitely want to have eventually. And it's not completely clear how to design this in a nice way.
So
and an efficient way.
So do you have like a mathematical model for this, or do you need to actually have new mathematics?
No, there's no new mathematics involved. In most of this, there's no new mathematics. It's just if you program these things, you will learn some mathematics, because very likely you don't know all of it. I don't. Yeah. I came up with an algorithm for this some time ago. So the algorithm is essentially straightforward. Okay, that's the first project. The second project is the following. So a group action is called transitive if for any 2 elements in my set, for any 2 structures, there is a group element which relabels one structure to the other. So all structures are isomorphic. Think of linear orders, for example. And then the corresponding species is called molecular. That's how the French called them, or the Quebecois called them. And it's then almost obvious that every species can be written as an infinite sum of molecular species. And this decomposition is also unique. That's, yeah, okay. That's how it should be. And every molecular species can be written in a unique way as an atomic species. So that's where the language comes from. And this decomposition is unique up to reordering, of course, because we're in a commutative setting. And I mentioned this already. Isomorphism classes of transitive group actions of a group G are in bijection with conjugacy classes of subgroups of G. So actually, what does this tell you? You can list all of them. So it's easy, or not computationally, but for the programmer, it's easy to list all species of given size, all atomic species. Atomic means you cannot write it as a product. Molecular means you cannot write it as a sum, and atomic means you cannot write it as a product. So for example, the singleton species is atomic, and linear orders is, x to the power of n without the sum is molecular. Another case of a atomic species is cycles, that's atomic. Permutations is not molecular because you can write it as a product. It's for each grade and even as a sum. Yeah. But this is nice because you can discover maybe you can discover interesting group actions. So in the past, group actions were something which you had a group, you had an object and you had a group action on it, and then you started the group action. But here we can systematically list all of them, which is quite beautiful. And 3 examples. So the action by conjugation, or a joint action, is for the symmetric group just a species of permutations. We saw this actually. Then the left regular action is just a species of linear orders. And then there is a relatively generic way, the action on cosets is the quotient species. Yeah, so it's just a name. But then it helps you because these help you because you can draw pictures actually. Yeah. And what I would like to have, so as a second project, it should be easy to turn a given group action into a species in Sage. So I define a group action using gap, and then I want to say, yeah, but I would rather have it as a species. That should be possible. Then, moreover, I would like to be able to decompose my species into the atomic, into a sum, and then I would like to give the decomposition of the species into atomic and molecular species. Yeah? And this is we have all the machinery is there. We just have to put it together. We just have to play a little Lego. And so this would be similar to, it would be the same, analogous thing of decomposing a representation into irreducibles. That's the same thing, just for group actions. And actually, this is a mathematical project, and I could give you some pointers if you're interested for this. So it would be very nice to consider statistics on group actions. But for this, group actions would have to be a combinatorial collection in Feinstadt. And mathematically, this is possible, but just nobody has provided a canonical form for transitive group actions yet.
Sorry, isn't there a gap database called small groups?
There is even a...
Isn't that
yes.
all group actions up to conjugation?
Yeah, for small group actions.
Right.
So up to, actually 1024 is excluded.
Yeah.
And so powers of 2 are excluded beginning with 2 to the power of 10. And it goes, I think, up to 10,000 or so. And that's not enough for Feinstadt.
Okay, but do you have a method to create a species from... okay, so you need a group action for every n, I guess.
Yes.
Yeah.
So I need a canonical form for every n. So actually, it might be enough to have a little less. But so the truth is, we want this. We want a canonical form for, or a canonical form in the sense of canonical form of a graph. So like naughty or bliss, just for group actions. And of course, we could also have groups in Feinstadt, but this is not so easy. So for a canonical form for groups is just impossible. This won't work. For group actions, this should be possible. So if you like to play with groups, with permutation groups, that's for you. And there are at least two more people who are interested, mathematicians, who are interested in helping you there. Okay, third project. There's an extremely nice generator for random structures. So if you have lots of structures, you would like to produce one of them uniformly at random, just to see how it looks like. How does a tree look like, a random tree? And there's a package that uses Boltzmann sampling, which is then, of course, called Usain Boltz, by Mathieu Dean and Martin Pepin. And well, they use, so their package, which is not in Sage, it's separate, they implement, so to say, a grammar, or they take a grammar and produce a Boltzmann sampler for it. And there's a lot of mathematics to do here to make this available for species, but this would be absolutely wonderful. So if you could define just any species, maybe you cannot cover all the operations, yeah, but at least sets of works, plus works, times works. Yeah. This is extremely fast. It's just instantaneous. You can generate trees, I don't know, size 50 or extremely fast.
So
It's completely generic.
what have they done and what do you want to extend?
So they do what they do. The input of the user is a grammar.
Yeah, but do they do it only for trees or they do it for
They
everything?
do it for everything. The input is a grammar.
Okay.
So
But then
they
what did you want?
specify you can use some operations
Yes.
like plus, times, and then special cases of composition, like sets of, and it just works.
So what did you want to do here? I mean, if they've already done it?
Merge this into the framework of species, so that it interacts. So if
But you're already defining it as a species, right? Yeah.
Yes, but now I have to, if I want to do the generating function, I have to do the same, just with a slightly different syntax. And the thing which is worst in on computers is do the same thing, just with a slightly different syntax.
Okay.
Just yeah. That's. Is there another question? Or? No. Okay. Okay, that's a difficult project, I think. It's not completely easy, but maybe actually I'm quite sure that these two would love to help. Okay, then yep. One natural extension of species, and an important extension actually if we really want to do research, is so-called multi-sort species. Or if you prefer multivariate species. You don't have one set of labels, but you have several of them, like labels in X, labels in Y, labels in Z, and then you would like to compute with them the same operations work. It should be a straightforward extension of the framework, but it involves quite a bit of work. But then you can do interesting things. You can define maps, you can define bijections, and so on. So to define the set of bijections, it's just one line, yeah? And you can list them. It's just one assignment. Okay, and the final thing, which is really for experimentation, you can define, I said a species is a sequence of group actions, and we said we use group actions of the symmetric group. But there are other groups you can play with, and the most interesting example would be the hyperoctahedral group or colored permutations. Why is this the most interesting example? Because you can multiply two group actions here. There's a natural notion of multiplication. For example, you don't have this for the sequence of cyclic group actions. There you cannot multiply. And also there is a notion of plasticity, a very natural notion of plasticity. In fact, there are two notions of plasticity which come very natural. And the difficulty here is to come up with good names. So for species, it works very well. A tree is a root. Is x times, how should we say, is a root times a set of trees. And for hyperoctahedral species, you get things like diagonals, vertices, and that's vertices of the cube and that sort of stuff. And it would be nice to have this implemented. And, and the very final slide is the sixth project, excuse me, I said 5. Group actions are sort of a refinement of representations. You can also do representations themselves. If you look instead, if you look at representations, and then you get functors from the category of finite sets with bijections to the category of vector spaces with linear maps. Would be nice to have this in Sage also, although I admit I don't have that many applications for this. So here the question is also, do we have real interesting applications? Yeah, and that's all I want to say. Thank you for being here. Very nice.